So we left off looking at the mole of reaction, and that delta H is a number of kilojoules per mole of reaction. So this delta H, we'll notice, is a positive number. This is an endothermic reaction, and in fact, this is the reaction from our endo-exo lab, the citric acid and sodium hydrogen carbonate. So let's take a look at what this wants us to do. We want to calculate the amount of energy absorbed that goes in, it enters the system in our endothermic reaction, when 345 grams of sodium hydrogen carbonate react with an excess of citric acid. And up here at the top, I do have the balanced chemical equation, as we'll need that to get our mole of reaction conversion. Again, it's important that as we look at this, we think about how our units fit together. I have 345 grams of sodium hydrogen carbonate, but my delta H is in moles. So the first thing I need to do is add up the molar mass of sodium hydrogen carbonate, which is about 84 grams. And then I need to get this 345 grams into moles, so I can deal with the balanced chemical equation and the number of moles of sodium hydrogen carbonate per mole of reaction. So of course, we take that 345 grams, we divide it by 1 mole over 84 grams, and I get that we have 4.11 moles of sodium hydrogen carbonate reacting. So now I have a mole. I can start thinking about how to fit that in with my delta H. I want to think about how do I get to the kilojoules here. Again, this is a case where we really have to look at our moles of reaction. So if I have 4.11 moles of sodium hydrogen carbonate, I can't go directly to this delta H step because the delta H is a mole of reaction. So I need to look at the balanced chemical equation. And now notice if I go one time through this equation, the way it's written, I use 3 sodium hydrogen carbonates. So for every 1 mole of reaction, I get 3 moles of sodium hydrogen carbonate. And I need to put this on the bottom on the opposite side of the fraction bar from my sodium hydrogen carbonate on the top. And then I'll have to put the mole of reaction on the bottom here to cancel that out. So this is so important, and why you should not skip it even when it is 1-to-1 is because if I had not taken care of that, I would have gotten a number that was 3 times bigger than what I should have. And that could be really important. So we do have a couple of other important delta H concepts. And really, we'll talk a lot about the fact that there aren't a lot of equations in this unit. There's really just using the delta H and then using our specific heat, which we'll talk about next. So one of the places we'll see this molar heat concept is thinking about melting and freezing and boiling and condensing, phase changes. And of course, melting and freezing happens at a temperature called the freezing point. That's the temperature at which we have both solid and liquid at 1 atmosphere of pressure. So for water, of course, that would be 0 degrees Celsius or 273 degrees Kelvin. At that point, we have what we call the enthalpy of fusion. And since it's an enthalpy, that's a delta H, and we write it as delta H of FUS to specify that that is fusion. And by convention, this is always positive. This is the amount of heat energy that I have to put in to melt 1 mole of solid at its melting point temperature. So melting is always going to be an endothermic process. That means freezing, the opposite process, is actually an exothermic process. So melting, endothermic, freezing is exothermic. And if you really think about it, it kind of makes sense. Something doesn't melt unless you put heat energy into it. So this number, this enthalpy, really depends on the attraction between particles, which is the intermolecular forces, which we'll talk a lot about in AP chemistry. For water, of course, as I said, the freezing point is 0C, and these numbers have been measured, and specifically for water, we could get it either in kilojoules per mole or in joules per gram. So kind of like R in the gas laws unit, this is a case where it's really important that we make our units match what we're given. If we're given a delta H in kilojoules per mole, we have to use moles of a substance. If we're given the number in joules per gram, then we have to make sure we're using grams of that substance. And we might have to do a conversion to make sure that those match. Vaporization is what's happening at the boiling point. Of course, the boiling point is the temperature where I have liquid and a gas at atmospheric pressure. And just like we have an enthalpy of melting and freezing, we have an enthalpy of boiling and condensing. And just like with the delta H of fusion, by convention, we always talk about this as a positive number, the amount of heat that's needed to vaporize 1 mole of liquid at its boiling point. And you know in your lived experience that boiling something takes putting in energy. If you're boiling water on the stove and you turn off the burner, the water stops boiling because you've stopped putting in energy. So vaporizing or boiling something is an endothermic process with a positive delta H. Condensing is in fact an exothermic process with a negative delta H. As if we go one direction with a process, it's endothermic. The opposite direction has to be exothermic. And again, the enthalpy of vaporization, that number is entirely dependent on what the substance is and what kind of attractions there are between the particles. And of course, for water at 1 atmosphere or 101 kPa, that is 100 degrees Celsius. And we can get a delta H of vaporization. And again, these come and we have to make sure we match our units. So this is 40.7 kilojoules per mole needs to be put in, or 2,260 joules per gram. And you notice this is a much larger number than the delta H of fusion. So let's take a quick practice problem or two using our delta H's of fusion and vaporization. So for example, we want to know how much heat energy is absorbed if we melt 47 grams of ice. And we know melting is endothermic. It takes in energy to melt. So we have a positive delta H. And when we look at the problem, we see that they gave us grams of water. So since I have two options here, I'm going to use the one in joules per gram. There's no real reason to have to go through another conversion factor. So I'll set this up and say, well, how much energy, how many joules is equal to 47.0 grams. And then I use my delta H of fusion. 1 gram is 334 joules, and that's going to be a really big number. So I'm going to go ahead and put it into kilojoules, so it's easier to round. And of course, 1 kilo anything is 1,000 of the base unit. So I end up with 15.7 kilojoules of heat absorbed. We can do a similar problem with the delta H of vaporization. In this case, though, we've only been given the delta H in kilojoules per mole. So we're going to have to make our units match. We must convert that 47.0 grams of water into moles of water, which is pretty easy to do. And again, boiling takes energy in. We have to keep the stove running to keep the water boiling. So delta H is positive. So we have one extra step here. We have to go from grams into moles. Once we have our moles, we can use that 40.7 kilojoules. Then we'll round it to 3 significant digits because of our 47.0 grams. So that gives us 106 kilojoules of energy absorbed in our endothermic process.